We're going to study now the notion of monotonicity. What does that mean? Well, suppose that you have a function that goes up, meaning if a is less than b, then f of a is less than or equal to f of b. Then it's called increasing. And if we can make sure that equality is never a possibility, meaning then this is called strictly increasing. Now, there is a some other possibilities for the terminology here. So sometimes people call what I called increasing non-decreasing, and what I called strictly increasing, they just call it increasing. And I think this is very good terminology, right to the point. But today we're going to just refer to functions as just increasing, and I guess in most cases we will mean strictly increasing. So in some sense, it's as if I'm actually adopting, oops, that's not what I wanted to do. It's as if I was adopting the second type of terminology. So sorry about this, a small okay, forget this C here. Okay, so when a function is going up, it's going to be called increasing. When a function is going down, it's going to be called decreasing. So if a less than b, then f of a is greater than or equal to f of b, then it's going to be called decreasing. And again, this is where some people would call it non-increasing. And if a less than b implies f of a is greater than f of b, then it's called strictly decreasing. And again, in other places, you will just find it as simply a decreasing function. Now, what we need to note here is that most functions do not do just one thing. They do all of these things at different parts. So for example, this function is decreasing here. It's increasing here. It's decreasing here. And finally, it's increasing here. And notice that every time it changes from increasing to decreasing or vice versa, we have a local extremum. Okay, so this is a local minimum. So when it changes from decreasing to increasing, we have a local minimum. When it changes from increasing to decreasing, we have a local maximum. So these are all interesting things to note. Now, of course, our goal here is to involve the derivatives. And this is precisely what we're going to do. So here's what is going on. Let f of x be a differentiable function on an interval I. Then if f prime of x is greater than 0, meaning for any x, then f is increasing on I. Or if you like, strictly increasing on I. And we're going to denote this way. And if f prime of x is less than 0 for any x in I, then f is decreasing on I. One thing that I didn't emphasize here is that this whole game with increasing and decreasing functions is played in the sense that we look at we consider the direction from the left to the right. So all of this terminology applies as we look at the graph of the function from the left to the right. So if it goes up from the left to the right, or if it goes down from the left to the right, then this one we call it increasing and decreasing correspondingly. And our goal is to try to figure out how we can use derivatives in order to find the type of what the function does. And we call that with one word, monotonicity. So monotonicity is the property pertaining to whether the function increases or decreases. And of course, the general picture that we expect is that the function will increase and decrease on different intervals. And that's what we mean by study the monotonicity of a function. So if somebody tells us to study the monotonicity of a function, then what we need to do is determine the intervals over which the function is increasing or decreasing. So determining the monotonicity of a function, or studying the monotonicity of a function, if you like, is the same as determining the intervals over which the function is increasing or decreasing. So how is this done? So first of all, the functions that we will be interested in here are functions that have that are differentiable and their derivatives are continuous. They're as good as one would hope they would be. And the ideal picture that we're going to have is that is something like this. So each interval of monotonicity is interrupted by a critical point, pretty much. But there's always the possibility that the function actually does not change monotonicity at a critical point. This is what the function x cubed does. So you have a critical point and the function does not have a local extremum at that point. And the way you would know that is because on the left of that point, it's increasing. And then on the right of that point, it's also increasing. So pretty much an extremum occurs when the monotonicity changes, meaning it goes from increasing to decreasing, in which case you have a local maximum. Take a look at that. Or it goes from increasing to decreasing, in which case you have a local minimum. Sometimes I like to say that the shape of a local maximum is the frown, the shape of a local minimum is the smile. So here's our plan. Our plan is we have a function, we find its derivative, and we find where the derivative is 0. So we find the critical point. And then we know that between any two critical points, the monotonicity doesn't change. So what we do is we take a sample point, a testing point in that interval, plug it into the derivative, and see whether the derivative is positive or negative. And from that, we determine what the monotonicity on that interval is going to look like. We encode all this information into a table that shows the behavior of the function very nicely. Why don't we do an example and see how all this works? So here's our first example. Determine the intervals of monotonicity of f of x equals x cubed minus 12x plus 4. Okay, so here's the solution. First thing is we take the derivative. And then we find the critical points by setting it equal to 0. So this is equivalent to x squared minus 4 is equal to 0, which means that x squared is equal to 4, which means that x is equal to plus or minus 2. So these are the only critical points. So if there are any changes in the sign of the derivative, we expect them to happen at those points. So here's what the monotonicity table is all about. We place the critical points on the monotonicity table, and we make two rows, one that corresponds to f, and one that corresponds actually to f prime in the beginning, and the one that corresponds to f. And we acknowledge that f prime is 0 at each of these critical points by marking them this way. And then what we do is we want to determine the sign right in between. So we go to the derivative and we plug in a number which is less than -2. Let's say, to exaggerate a little, let's say that you plug in 100, right? Then you get a huge number, so you get something like 30,000 right here, minus 12. And you didn't have to plug in such a big number. You could plug in -3, and then you would have got 27 minus 12, which is 15. So that would tell you that the derivative is positive here. Then you plug in a number between -2 and 2. Here we have a very obvious choice, the number 0, and that will give us -12. Again, you have to be careful. You plug those into the derivative, because what interests you here is the sign of the derivative. I'm saying this to clarify that this is not what happens in the case of the the optimization over a closed interval. This is where we were plugging points into the function, not the derivative. In any case, let's go back to -2 to 2, to the interval from -2 to 2. We plug the, we take 0 as our testing point. We plug it into the derivative. We find -12, so it's negative here. And finally, if we choose something greater than 2, so again, we can choose 3, we will say once more that it's positive. So the intervals of monotonicity, then f is going to be increasing here, decreasing here, increasing here. And an interesting piece of observation that was not, we were not asked to produce anything like that, but it's interesting to notice this, is that this is a local maximum and this is a local minimum. Okay, now we still need to give our answer in a nice way. So we will say that f is increasing from -infinity to -2. And we can actually, since we have a continuous function, we can always take the interval to be closed. F is decreasing on the interval from -2 to 2, and f is increasing on 2 to infinity. I could have written this in a more concise way as f is increasing on -infinity to -2, f is decreasing on -2 to 2, and f is increasing on 2 to infinity. The one thing that I want you to notice here is that some people might be inclined to actually take these two, since it's increasing in these two intervals, and say something like f is increasing on the union of the two intervals. In general, that will not even be true. So just avoid putting non-adjacent intervals together. If you knew that it was increasing on two and adjacent intervals, then you could actually deduce that it's increasing on their union as long as it's continuous. Especially what matters is the point where those two intervals meet. But in general, like it is in this case, you should just leave it alone and keep the intervals separate. Okay, let's do another example. So this time, let's choose a slightly more interesting function. So example. Determine the intervals of monotonicity of f of x equals x over x squared plus 1. Okay, let's see what happens here. So let's begin by taking the derivative of this function. So this will be x squared plus 1. Sorry about this. So this will be 1 times x squared plus 1 minus x times 2x over x squared plus 1 squared. This is the quotient rule. So this will give us x squared plus 1 minus 2x squared over x squared plus 1 squared, which is 1 minus x squared over x squared plus 1 squared. And you see here another example where if we were just interested in finding the derivative, then we won't have simplified the result. But here we specifically want to find, we want to do things with the derivative. So it's in our best interest to simplify it as much as possible. And now we need to find the critical points. So we set the derivative equal to 0. This is equivalent to 1 minus x squared over x squared plus 1 all squared being equal to 0. The only way that a fraction can be equal to 0 is if the numerator is equal to 0. So this and 1 minus x squared is equal to 0. And of course, this means that x squared is equal to 1, which means that x is equal to plus or minus 1. So we have plus or minus 1 as our two critical points. So we set them on our table. Here's the first row, representing f prime. Here's the second row. We know that on each of the critical points, the derivative is 0. And then we want our testing points. And remember, we're going to plug in the testing points where into the derivative, into this, right? Notice that the denominator is always positive and it's of no consequence. So we want to plug this into the numerator. And let's start with the first interval on the left. So just take -2. If you plug it in, you will get, on the numerator, you will get 1 minus -2 squared, which is 1 minus 4. It's -3. That's a negative here. And then if you, for the middle interval, you can take 0. You see, I'm not even writing what the testing point is. There's, no need to show this work. If we take 0 and we plug it in, we will get 1 minus 0. That's 1, which is positive. And finally, if x is greater than 1, then we want to take a number like 2. If we plug it in, we will get 1 minus 4, that's -3 on the numerator, and that's negative, which means that the function is decreasing here, increasing here, decreasing here. This is a local minimum, and this is a local maximum. And now we can give our answer by saying that f is decreasing on the interval from -infinity to -1 closed. F is increasing on the interval from -1 to 1 closed, and f is decreasing on the interval from 1 to infinity. Please note that the intervals from are left with their open, the parentheses at the infinity points always, because infinity is not a number, it's just a symbol that allows us to go to arbitrarily large or arbitrarily small numbers. Small, I mean arbitrarily large negative numbers. Okay, so why don't we do one more example with some slightly different function. So find the intervals of monotonicity. Of f of x is equal to x times e to the negative x. Okay, so let's see how we do this. We take f prime of x to be 1 times e to the negative x plus x times e to the negative x times -1. Notice that this is the derivative of x. This is the derivative of e to the negative x by the chain rule. And how do we find the critical points? So to find the critical points, we set the derivative equal to 0. And we can factor out e to the negative x, and what is left inside is 1 minus x. And we set this equal to 0. This is never 0. So the only way that this can be 0 is if you have 1 minus x being equal to 0, which means that x equals 1. So this is the only critical point that we find. X equals 1. So we have f prime, we have f, and we know that f prime is 0 right here. And we take now a testing point. Where should we plug in the testing point? Actually, in the simplest expression for f, which is this one. For f prime, which is this one. And this thing is always positive. Again, we can ignore it. And the only thing that matters is 1 minus x. So for example, if we take x to be 0, which is on the left of 1, we will find 1 in that parenthesis. And this means that this is that the derivative is positive on the left. And if we plug in 2, which is a testing point on the right of 1, we will find negative 1. And this is negative on the right, which means that the function is increasing here and decreasing there. And here there's a very interesting remark, right? I mean, I'm about to say that this is a local maximum, but there's something more interesting here. I mean, think about it. The function just goes up and then it goes down. It never turns again, right? What does that mean? That means that this is actually a maximum. It's not just a local, it's a global maximum. It's one of those wonderful cases where we can say a little more. And the final answer here is, of course, that f is increasing on negative infinity to 1 closed, and f is decreasing on 1 to positive infinity. And that's it. Okay, thanks for watching this.